Okay, welcome to another edition of the Jayashree seminar. We have a pretty full seminar series this semester again. It's coming up next week. We have Mark Johnson from Brown, followed by Jordan Cohen and Mark Lippman and so on. As usual, the schedule page. I encourage you to go look at it and see what else is coming. Today we are going to hear from Dr. Jayashree Subrahmonia. She is the manager of the Pen Technologies division at IBM's Watson Research Center, and her group is responsible for some of the interesting handwriting products that come out of IBM. Today she's going to talk to us. Her talk has a fairly generic title, Putting Pen to Smart Paper, and she's going to tell us a little bit of introductory things about handwriting recognition and then talk about some specific research in it.
Thanks. I guess I'm audible across the room. First of all, thanks to Sanjeev. I've enjoyed visiting Johns Hopkins, and as you mentioned, I actually manage a group that does large vocabulary unconstrained handwriting recognition. I'm actually not part of the larger speech group that you're probably more familiar with, even though we have very close interactions with them. What I'm going to talk about today is, let's go to the slide projector here. Okay. So, the title of my presentation today is Putting Pen to Smart Paper. Actually, if you look at the major differences between speech and handwriting, one of the problems that we've faced for a long time is the lack of an interface to get handwriting data into the PC. The speech world actually has been fairly lucky in the sense we have a microphone to get audio into the PC, and you talk in front of a microphone exactly as you would in real life. Unfortunately, with pen, we've not had the luxury of having a platform that has the natural pen on paper interface, which is something that we're all very comfortable with. We all learn to write on paper. So a natural way to input handwriting into a computer is through an interface that has a natural pen on paper medium to get the handwriting data in. So one of the things that we've been working on in my group, in addition to developing technology for large vocabulary unconstrained handwriting recognition, is also to worry about the platform to get that handwriting data into the PC. And about 4 years ago, we developed technology called ThinkScribe, which is, and this is what it looks like, and it's a piece of hardware on which you can put any regular pad of paper, and you write on it with a special pen that looks a lot like a regular pen. It's just that the pen has electronics in it, and so has the piece of hardware here. And it's the combination of the two that allows users to use a natural pen on paper interface to get your handwriting data into the PC. We marketed this through AP Cross, that makes the company that makes pens, and it's been in the market for about a couple of years now. So a lot of my talk today is going to be structured towards actually talking about this piece of hardware, which actually forms a very significant component of the work that we do, and in addition, then I'll talk about the handwriting recognition technology that comes packaged with this. And in looking at the handwriting recognition technology, I'll actually focus more on the major differences between pen and speech, because you have a fairly significant strength in the use of HMMs for speech. So what I'd like to do today is highlight the major differences between the two. And so my talk today is actually going to be structured as follows. I'll give you a brief overview of pen computing and talk a little bit about this piece of hardware. Give you a demo of ThinkScribe, which is this piece of platform, and then go on to talking about unconstrained handwriting recognition, which is what my group in particular works on. And here I'll give you an overview of the models we use, how we train them, how we decode them, how do we customize them, and then probably point you to future work that we are doing in the area of pen computing in general. And feel free to stop me along the way if you have any questions. So the question is, people keep asking why pen? I mean, is pen really essential for interacting with the computer? And even today, I think it's still the most convenient form of input for things like gestures, drawings, and so on. In addition, in meetings like this, obviously audio is not the best form of input, it's handwriting to capture information that's going on. So it's private, so in cases, for example, if you're on an airplane and you want to write a piece of email or something, then you still want to probably use pen over speech because it still maintains privacy. So there's still a lot of cases where pen is pretty much the the one mode of input that you would like to use to input information into the computer. Now, so the question is, what is ThinkScribe? The group that I'm in, which started working on large vocabulary unconstrained handwriting recognition in probably the 1993-94 timeframe. And what happened was for 3-4 years, we worked on this technology. And at that time, IBM used to make one of these ThinkPads, which had a screen on which you could actually write, so you could write on glass. And what happened was when we actually ran some market group research surveys, people hated that because writing on glass is not natural. It's not something we feel comfortable with. It's not the right medium, to input large quantities of data, so pages and pages of information. So pretty much IBM discontinued working on that line of ThinkPads. So we didn't have actually a platform at that time to get this data in. What were the other kinds of platforms? Well, the Apple Newton was available at the time. And it did a great job what it did, but again, it's not the right interface for inputting large quantities of data. The glass interface, again, which is not something people feel comfortable with. There are, I'm sure a lot of you have seen tethered tablets, where you have these tablets by Wacom, that you connect the tablet to the PC, and you write on the tablet as you're looking on the screen. Extremely unnatural. I mean, you're constantly looking for feedback on the PC screen while you're writing on the tablet. So what's been the most successful actually has been the Palm, which was, has come to the market about a couple of years ago. And for what it does a great job. So it's meant to be a platform to input small quantities of data, like memos and appointments and to-do lists and so on. It does a great job at that. But again, it was not the right platform for writing large quantities of data. So that's when we came up with the idea of this, of the ThinkScribe. And what it is it's a digitizer underneath this pad of paper. And so you put a regular pad of paper. The digitizer itself can sample points at 254 dots per inch. So it's a fairly high-resolution tablet. It actually is capable of sampling at 1,000 dots per inch, and we just use 254 for recognition purposes. The pen itself has actually electronics in it. So if you open it up, there's actually a small transmitter inside the pen, and it's powered by a quad-A battery. So what happens is when you actually write on this pad of paper with a pen, this transmits a signal that's actually being sensed by the pad underneath here. The data is recorded as XY as a function of time. So as I'm writing on this, the coordinates of the points that I write, which are sampled at a resolution of 254 dots per inch and a frequency of 133 hertz. So you're getting 133 points per second. And those points are stored as XY as a function of time on this device here. The device has 2 megs of memory on board and can store about 50 pages of data. So because it's highly compressed, so we Huffman encode the data points to store it on this device here. Also, the device itself has a NEC processor. So actually we would like at some point to evolve this into a platform that can do more than just data capture, which is what it does today. Today it's just a dumb data capture device. Ideally we'd like to do actually more on the platform, kind of absorb some of the functions that you see in the Palm, probably on the device itself. So we're actually thinking of evolving this into a platform where you can put a real-time operating system on this and run applications on board as well. The device itself comes in 2 form factors. There's an 8.5 by 11 version and a 6 by 9. And I'm actually going to show you a demo on the 8.5 by 11. The device, just as you have multiple notebooks in real life, you can have multiple digital notebooks on this device here. So what you do is you can, as you're writing information on pieces of paper, you can assign them to different notebooks. And essentially when you then transfer that data to the PC, it'll just put them in the appropriate notebooks that you've assigned them to. The device communicates to the PC using a USB IR or a serial connection. So those are the 3 modes in which you can transfer the data to the PC. The PC has all the smarts to actually do anything with the ink, like recognize it or archive it and retrieve it. So this right now is just a storage device. It doesn't do anything more than that. When we essentially evolved this into a platform for doing notes archival and retrieval. So the idea here is you take your handwritten notes and you want to be able to archive and retrieve them effectively. So the way we decided to do that was to mark keywords or tags in your document. And you do that by actually circling the words that you want keyworded. So you write a word and you tap on one of these buttons and you circle the word that you want keyworded. And that essentially assigns a tag in the data stream to that portion of ink. So at minimum, all the tags in your document will be transcribed into text using the recognition software. And over and above that, you have the option of doing more recognition if need be. Okay? And finally, so this is actually, it's a PC companion. It allows you to index and view your documents. We also have a flexible API and a toolkit that we make available to third parties to write applications using this device. Okay, and the two versions that came out actually, so the new version has the NEC V850 processor. It has 2 megs of memory. It actually comes in two forms, one with 2 meg and another with a meg of flash. It has 128K of ROM, which has most of the firmware in it, and then 4K of RAM as well. So these are the new piece of hardware that you're actually going to see. The software itself that comes with this has 3 pieces to it. There's a piece that actually communicates with this device. So we call it the ink transfer. And how many of you are actually familiar with the palm? I guess a lot of you, right? So it's analogous to the hot sync that you get on the palm. So it's always running on your PC, it's waiting for data to come in. There's IBM Ink Manager, which actually I'll show you right now, that contains the software for doing the archival retrieval. And then we have the Ink Manager trainer that we use to train for users' handwriting. Again, that's very similar to speech. We have users write predefined sentences, and then we train writer-dependent models using that. Okay. Actually, I just wanted to put this slide up before I go over to the other side. So essentially, the pen works as follows. There is a pen barrel, and there is actually an RC circuit inside that. So when I press the pen tip, the switch actually closes and emits a different frequency that's actually sensed by the device underneath. Now, this is the kind of technology that is fairly state-of-the-art today to capture high quality of input. However, if you look at the pen itself, this whole area is actually evolving, and there are people who are working on the next generation of what these electronic pens should look like. And probably the next device would look like the following, where you probably would have a clipboard with an array of sensors, and you wouldn't have this hardware digitized at all. And the pen using triangulation would measure the XY coordinates. And then the next version after that would probably be one where the pen has an accelerometer inside it, and it measures the acceleration and uses that to compute the displacement between points. So those are the directions in which the pen technology itself is evolving. And actually, part of my group is also responsible for thinking about next generation pen platforms. So that's another area that we actively look at. The area of handwriting actually is one that has been, you all probably are very familiar with the big players in the speech. So I just thought I'll point you to some of the big players in the pen arena. So there's a lot of work that goes on in OCR, offline character recognition, and what we do is actually online systems. And typically in the online area, there has not been as much work because of the lack of a good platform to get this kind of data in. Our biggest competitors are actually Paragraph, who's right here, and Lexica, which is part of Motorola, which Lexica is also a speech company. And these are two companies that have large vocabulary unconstrained handwriting recognition software. And if you're all aware of the Apple Newton, the handwriting recognition technology that they have is part of Paragraph. So Paragraph and Lexicus are the two big competitors for us for doing large vocabulary and constrained writing. And there are other smaller companies like CIC and like the Palm, Graffiti, Art, and so on that do isolated single-stroke recognition. And there are a number of people who are actually working on other electronic pen platforms. So there is ePen using this ultrasonic, the triangulation-based techniques, and other companies like British Telecom and LCI who are also actively working on building the next generation pens. Okay, I'm going to go over now and I'll show you a quick demo so that you can get a better feel for what this thing does. So actually, this is the 8.5 by 11 version, and I typically use this to take my handwritten notes. It differs from the 6 by 9 in that actually there are two sliders on either side, and you can use the sliders to indicate the notebook name. And every time I sync this pad to the PC, it'll download my active notebook names. Okay, so in this case, I've taken a bunch of notes, but in particular for today, I've taken a page of notes here where I've written some data, and I marked keywords by actually circling the words that I want keyworded. Okay, and all I do is I've connected this thing to the PC. And there's the hot sync equivalent of this that's running. So with my pen, if I now say, upload the data, okay, and it actually transfers it up, and it's about the time that it takes to transfer the data. Once it's transferred, what it does is it looks for all the tags in my document and recognizes them. And once it's recognized that, then it'll put it on it'll open up this application, put it in there. Okay, so actually, this is a little bit of juggling that I need to do here. Okay. So, actually, I want to go back to my desktop, but using. Okay, so that's the notes. These are the notes that I took today. Okay, that I showed you. So what I did was, right now I have all my handwritten notes on the PC. The items that are marked in blue are actually things that have been converted into text. So, things like smart paper and handwritten notes. And here I've actually trained the system for my handwriting. So it's using that in conjunction with the data that's been transferred to do the recognition. On the left-hand side, you see all your active notebook names. So at any point when I sync it up, it can actually download all the notebook names that I'm actively working on. We have a notion of what we call as on-pad notebooks and off-pad. So things that you're not actively working on, you can move to the off-pad notebooks. So I'm actually, now at this point, I have my handwritten notes in the PC, and I can look at them in different ways. I can actually retrieve them or index into them using keywords. So for example, if I click on the keywords tab, it tells me that these are the 3 keywords that I wrote. These are the ASCII transcriptions of it. These are the time and the date stamps and the notebook names that was put in. And similarly, I can look, in this case actually I don't have, I'm going to pick a notebook. So I can look at my appointments. So here I said meet Paul, and then you can look by date or look by to-dos. Okay. So, so for example here it says search for keywords, and if I click on that, I can go to that to-do. So essentially, to-dos, keywords, and appointments are the 3 kinds of tags that I can use to tag pieces of my ink. This piece of software also actually communicates with the Palm desktop, so that if I do have a Palm installed on my PC, I can take all my to-dos and appointments and dump it into my Palm desktop as well. So essentially, I can do that. I can also look at my notebooks by date or calendar. So I can say, give me all the notebooks that notes that I took closest to. In this case, actually, these are my notes that I took closest to a certain date, and I can actually go back to that my notes that were taken at that time. So essentially, that's what the piece of software does. It gives you a way to take your handwritten notes on this device, upload it to your PC, and you can use as much as little of the transcription recognition technology to be able to convert portions of your handwriting into text. Okay? So I'm now going to move on actually to talk about some of the, put this back. Okay. Let me go back to talk about the recognition technology itself, and here's where I'm actually going to focus a lot on the modeling itself. Okay. So as I said, we have our handwriting recognition software is unconstrained handwriting. It's cursive printed combination of the two, large vocabulary. So the system ships with a 40,000 word vocabulary. We use word level unigrams and bigrams, and when you use an out of vocabulary mode, you use a character level n-grams to do the recognition. So these are typical samples of handwriting that we need to recognize. So here I'd like to highlight some of the major problems that we encounter. First of all, the variability that we need to handle is like you've seen here. There's some people who write extremely neatly. They pick the pen up between 2 letters. But there are others, who write like this, where you probably don't even see the ER, for example, in either very clearly. One of the big problems we face is people never write on a baseline. So a lot of our features are actually scale dependent, and one of the things we need to do is estimate baselines and sizes. This is usually a big problem because people don't adhere to a baseline. You typically find people going up and down and so on. So that is one of the major problems. people come back and dot their I's and cross their T's all the time. So, this is a case where you're actually coming back and, you're adding ink, if you might, to portions of letters that you've already written. And because in this system you can go back and insert words anywhere that you want, typically people would, write the first column, they'd come back, insert a word in there, go back and make changes and so on. So there's a lot of this, non-causality because people are coming back and making changes that happens, which complicates matters immensely for us. A lot of variability in letter shapes that, even between a single user. So we find that even for a single writer, the variability between training and test data, is a lot. So typically, after they train, if they're really tired or something, the handwriting style changes considerably. So you need to be able to account for that. So these are some of the major problems that are very specific to handwriting that we need to address. This is the overall scheme, and I'm going to talk about each particular module as I go along. A lot of these are very similar, as I said, to the speech system that you are used to. So I'm going to focus in more on the differences here. So the crosspad essentially gives out X, Y points that are ordered in time. It then goes through a module that has normalization and feature extractions. So in the normalization phase, what we want to do is we want to be able to recognize an A if it's this small or this large. So essentially this module normalizes for size, so that then when you do the feature extractions, they are non-sensitive to size changes. Then those features are sent in through search, so we have a fast match scheme and a detailed match scheme. But then handwriting essentially is a two-dimensional entity. So even though the online scheme has time-ordered sequence of points, we actually would like to use image-based features because a lot of human recognition of handwriting is done visually. So in order to augment, to refine our results, what we do is we go back and we look at OCR kind of features. So we rescore our n-best list at the end using OCR features and use that to come up with a final set of answers. Language modeling, again, so we have a 40,000 word dictionary, so lettered word unigrams and bigrams, and character n-grams. So actually what we do typically in systems like the ones that I've shown you is we use a very small beam n-gram search that's running in parallel with our dictionary search. So typically users write in vocabulary words most of the time, but occasionally when they do write a word that's not in vocabulary, you'd like to be able to pick it up. So we actually run both of these in parallel. Finally, now we've actually been looking at more of the finite state grammars because we've been looking at forms applications. So one of the big uses of this is for people filling out forms data. So you want to be able to use much more of the constraints within an entire field to be able to improve recognition accuracy. So we've been using finite state word grammars for that. So that essentially is our suite of language models that we use. So now I'm going to move on to pre-processing. So task one, once that data points come out of the crosspad, the first task that we need to do is actually segment a page like this into regions, each one of which either you have text or you have something like diagrams or block diagrams. Right now we don't do anything with block diagrams, so they're just left as pictures and images. So only thing that we know to deal with is regular text. So that's the first use of this task. In addition, as I said, we need to do normalization. Normalization is easily done if you have more words that you could use to estimate the normalization factor. So typically, for example, in the case of these bulletized lists, people would put the bullets in sometimes and then go back and fill in the text. If we were to look at it as just a sequence of XY points coming time ordered, then you would first, you would be looking at the dash here and then followed by the next one and so on. And you can normalize this data. So what you would like to do is look at a page like this and reorder all the strokes so that things that do belong on a line are clustered together. And then once that's done, then you have enough information to do your normalization and feature extraction for that. So now points come out of the tablet at 256 dots per inch, 254 actually, dots per inch. Then we do a filtering to remove some of the outliers and noisy data points. This is when the pen switches sometimes, doesn't close completely, so you have these jitter. Once the points come time ordered in X, Y. We really don't care about the timing itself as much as the ordering. So if the person writes really fast, we'll have fewer points in there. If they write slowly, then we have more points. So what we do is we'd like to go back and resample the data so that you actually fill in points where there aren't enough because the person actually wrote very fast. And the way we do that is we take the original set of points, we fit a cubic spline to it, and we go back and resample the data equispaced in space. So what starts out as a set of points that are equispaced in time is now converted into points that are equispaced in space. Once that is done, then what we'd like to do is go to those points and estimate these 4 lines, which are called the baseline, the midline, the top line, and the baseline. This is not easy to do, especially if the person is writing, like this, where the person is not sticking to a baseline itself. In the case that I've shown, this is very easy to do. It's very clean data. And the way we do this is we project all the data points onto the y-axis, and then we look at a histogram of that and use that to compute the four different axes. But the histogram is typically very, very noisy, and there are a number of things we do. So we maintain a history of normalization factors and use that to actually guide our normalization as we're going along. We also allow for non-straight line baselines. So we actually look at piecewise linear baselines so that if people don't typically write on a straight line baseline, we are able to correct it as we're going along. Okay, so once the next thing that needs to be done is the equivalent of your set of phoneme identification. So in handwriting, people write letters very, very differently. So, and there is no way for us to actually know a priori what are all these shapes that people can write. So essentially, it's something that you need to learn from training. So here's just one sample that illustrates the variability in shapes that we can see. So for example, if you look at a lowercase a, it could be any one of these different shapes. And actually, I'm just showing you a very small subset of the variability that we typically see. So typically, you actually have 20 to 25 different variations that you see in each one of these letters. Now, unfortunately, since our models are a function of time, if a person writes the same letter the other way around, that's actually a different model for us right now. So essentially, there are a number of different shapes that you can see for each letter, and you need to learn this automatically from training data. And so the way we do this is traditionally, the way we were doing this was actually treating the process of shape identification separate from the HMM system. So what we would do is we collected a lot of discretely written letters like this, and we would convert each one to a string of dimension 40 and do clustering in that space. That's what we did. And that was completely an offline system, and that once that was done, then we would train the HMM system on a completely different set of features. So things didn't work well, and also we were stuck with the fact that we needed discrete characters. So ideally, we would have liked to work in the same space where our HMMs are built. So we have, so right now what we do is we go back, we actually use a HMM k-means scheme. So here's what is done. So for each, let us say this is the sequence of letters that you have in your training data. Then you go and you randomly segment it into n clusters. You build an HMM for each one of those clusters, you relabel, and then you go back and re-estimate your HMMs again. So essentially what happens is you let the system learn how many HMMs there are in this in your space of A's. So for example, if you find that there are 2 different shapes of A's, what you do is, let's say you initialize the system with 10 different HMMs. So you randomly segment your A's into 10 HMMs. You build it, you relabel each A to the closest model that based on likelihood, you go back and retrain and so on. And at the end, what will happen is many of the models will start looking alike, and we use a likelihood ratio test to decide when to merge 2 different models. So essentially, it's done as a combined HMM k-means scheme. And I can give you the details of that if you're interested. So at the end of that, what you have is we have a list of all the unique lexemes, as we call them, unique shapes in our set. We start out with 93 different lexemes, 93 different characters. These are all your keyword all the symbols on your keyboard, and the number of lexemes we get are typically about 250 for that. So there are 250 unique shapes of writing the 93 letters on the keyboard. Now, feature extraction. So now what kind of features do we look at? So for each one of the letters, we assume that all the information in the letter is actually contained near the singular points. So what we do is we take all our letters, we identify the singularities and the extrema points in this letter, and we only keep all the information in a window around these points. And we throw away everything else. So we've actually done experiments where initially we were keeping all the points in the data, and we had the sliding window frames, so very much like speech. We would take the first 10 points and then have another window that's slid over and so on. And we found that there's not much of a reduction in accuracy when we actually go to a scheme like this, where we only keep information in windows around the high curvature points. Okay, so for each one of these, we extract at the tangent and the curvature information. This is for our first level of processing. So this is delta x, delta y, delta sine, delta cosine, and absolute y coordinate. In addition, actually, recently we've been looking at some of the wavelet-based features for some of these pieces of characters, which actually has been giving us slight improvements. But in the system that actually ships with this, these are the kinds of features that we use for one of these windows. Each window has 41 points. So we get, for every 2 pairs of points, we actually compute these features, and that gives us 205 dimensions. We use LTA to project that down to 9 dimensions. And that's the feature space that we work in. So each frame here consists of 9 different features. Okay. Okay, we have a single HMM per lexeme. So for each lexeme, we have a separate HMM, and they all vary in the number of states. So what we do is we look at the mode of the distribution for all the frames for a given letter, and that decides the length of the HMM. So typically, you have your uppercase letters would have a longer length compared to something like a lowercase I. So the length of the HMM is also learned during training. We started out using an HMM topology that is very similar to the speech HMM topologies. Where you have your typical left to right HMM, you have your self loops and skip transitions. However, let me point out that this kind of topology actually doesn't make that much sense for handwriting, because the rationale, for having self loops is that you can have a sound that's either, a shorter duration or a longer one. There's really no analogy to that in handwriting. So we've actually been looking at other topologies where what we do is we remove the skip and the null transitions, and we build an HMM for every length that we see in the training data. So if you see an A with length 3, 4, and 5, you will build an HMM of length 3 for an A, 4 for an A, and 5 for an A. So, and then we train that system up, and then we might decide to share states if they are very similar. So we've actually been looking actively at this and this whole topology issue, because inherently, I think this is one of the big problems when you look at handwriting, is that this really does not model what you're looking for very well. Yeah.
So what determines the number of
states? The mode of the distribution of frames. So we take all the A's in our training data. We compute the number of frames.
Extremities is number of states.
Number of extremities. Right. Each extremity gives a frame. So for every letter in the training data, we compute the number of frames. We compute the histogram of that, and we look at the mode of that distribution.
And what is the variance of this?
Typically, actually it varies from, lexeme to lexeme. Off the top of my head, I don't remember. Let me tell you, typically for lowercase, the length changes over 3 or 4. So you're talking about, the variance is about 4 standard deviation, right? So that is the norm, typically. So it's not more than that. Okay. So what are the parameters we have? We learn the number of states for each lexeme. we have a completely tied mixture system. We have actually semi-continuous HMM. So we have a tied pool of 750 Gaussians that they all share. And in addition, we have a, typically 5 to 10 Gaussians if we play with it for each HMM that is actually specific to that. So that's the system that we have. So it's a tied pool of 750 Gaussians plus a smaller set of 5 to 10 Gaussians that model the individual lexemes. In addition, and then the other parameters that we actually also estimate are the lexeme length distributions, like I showed you, the number of things like number of ascenders and descenders per lexeme, number of delayed strokes per lexeme. Okay, let me tell you, so delayed strokes are things like dots on your I's and crosses on your T's. Okay, now this is a big problem for the HMM. So how do you train a model for a T that has a cross on it? I mean, there is no delayed strokes because people can come back and cross their T's much later. And typically people come back, actually this is a very common phenomenon where people would write something like this and they come back and write their T all the way at the end. So you don't know which piece of letter this actually belongs to. So the problem of assigning the delayed stroke to the body stroke that it actually belongs to is a non-trivial task. For the fast match, what we do is we just take the frames of the delayed strokes and we sort them in with the letters, because for the fast match, they're all lumped into one state. So we really don't care about the time sequencing. For detailed match, what we do is we build separate models for the delayed strokes. So in addition, we strip out the delayed strokes from a T. So a T model would actually be built like this. And in addition, we build models for the dashes and the I's. So when we hypothesize a T, essentially we have to also account for the score for the delayed strokes and the dots and the dashes. Okay. And the training is done typically using, a Viterbi or a forward-backward training. The search itself is a time-synchronous beam search. So, and the only difference I wanted to point out is essentially when we hypothesize a certain letter, we look at the length distribution. So we know if we know that a C can have anywhere between 3, 4, and 5 frames, we don't look at anything else. We just expand all the letters with that distribution. Okay, so before I move on, I'm going to show you some results. So this is some data that was trained on 200 writers. We had 150,000 isolated characters and about 100,000 words. And this is tested on 1,250 words collected from 20 different writers. I must say that we have not had the luxury of having a consortium like you have that's used to evaluate different systems. So this has been very unfortunate. There is a new effort that's called UniPen that has just started, where we're actually collecting data across different organizations, and it's being coordinated out of Netherlands. But there have been no standard evaluation that have been done so far. Yeah.
So you had 1.5 characters per word.
1.5. Pardon? No, 150,000 isolated characters plus 100,000. Yeah. And typically the error rates with this on this data set, you start out with something like 30% error rates for your fast match, and then eventually when you use detailed match with Unigram, you get about 20%, goes down to about 20% error rate. And don't look at these numbers, but I just want to put this up because I'm going to talk to you a little bit about the writer clustering and adaptation work that we do, and I'd like you to compare these numbers to what we have, because that essentially is the same system that's used for adaptation.
This is measured at the word level, or?
This is word level. No, not at the character level. Actually, the n-gram is measured at the character level, the detailed match n-gram. Okay, writer adaptation. This is another place where we actually, we've spent a lot of time doing writer clustering. Okay, so writers there are a number of different styles that we see in our training data, and ideally what we'd like to be able to do is cluster these into styles that are very similar. In speech, and correct me if I'm wrong, it's typically done by fitting a small set of Gaussians to some of the speech data and doing bottom-up clustering. That's one of the popular techniques that people seem to use. And a lot of you typically look for patterns like male versus female and so on. And there's no equivalent of that in handwriting really, and many of those schemes actually didn't do very well. But what did work very well was the following. We used what are called, each writer for us lives in their own LDA space. So each writer has a trained LDA space that's specific to that writer. And we look at what's called as a principal angle between these LDA spaces. And we use that to do our writer-dependent clustering. So essentially, there is, if F and G are actually two subspaces of dimension P, then you can recursively define what's called as a principal angle as is cos theta of K. And actually, there is such a notion as a distance between these two spaces that is given using these principal angles. So we compute this distance between F and G as the sine of theta P, and that is used for us to bottom-up cluster our individual writers. And actually, this is one case where I found that this scheme has actually worked much better than any of our clustering schemes using the data and the model itself. So it seems like the space that these writers live in contain a lot of information about their writing style.
Are the LDA target classes in the writers? You need some classes for LDA.
So we have a training data. So we have 100 writers who have written training data. So what we've done is we've trained up a system for each one of them, and each one has their own LDA space at the end of it. So what we do is we have these 100 LDA spaces, and we bottom-up cluster them using these notions of principal angles. And that gives you a subset of the writer styles that users use. And so I'm going to actually, before move on, I'm going to show you an experiment where we collected data from 113 writers. And the training data is typically one where we provide people with these training data pads, writing pads with sentences like this that they're asked to write. And we've actually crafted these sentences. We spend a lot of time in crafting our training data so that we can get a lot of the character bigram coverages in the training data set itself. So we actually spent a lot of time capturing, designing this training text so that we can capture most of the character bigram coverages in the training data itself. So we have 120 sentences that each one of the training writers has written. And then we've held out, so in this case, each writer was asked to write 120 short phrases, which could be used as training data, and they were asked to write 120 phrases to be used as test data. And then for all the experiments, what we did was we held out the 13 writers as a test set, and I'm going to show you some of the experiments on that using the rest of the 100 writers as our training data sample. So what we did here, is the following. We built a writer cluster, 10 different writer clusters from 100 writers. So 100 writers are actually clustered into 10 different clusters. And using this, the notion of principal angles. And for each one of the test subjects, we look at the test data and use that to identify which cluster it belongs to and decode using the HMMs for that. So we found that using a set of, this is 10, so here's what we did. Using 10 words from the test data, we actually identify the cluster, and then we go back and rerun the decoding using the cluster that actually picked. And we find that on an average, if there's a reduction of 41.42% in error rate when you actually do a full writer-dependent training, you get pretty much half the way when you do a writer cluster identification and the decoding using that model. So essentially what happens is if you have all the data from 120 sentences from the writer and you can bootstrap that model and train, you get a reduction of about 41.42% in compared to a writer independent system. Whereas if you actually do the writer cluster identification and do a decoding on that, you get about 30% reduction. So you're pretty much going more than half the way towards doing full writer dependent training. Okay. All right. So, writer-dependent training. This is, since we have a small set, we have a 750 Gaussian system, so we do not, our writer-dependent systems actually have fewer Gaussians, so they typically have 4 to 500 Gaussians, depending on the task. So we are actually able to bootstrap these models from scratch and train them up. So what we do is we collect training data from the users actually copying sentences on these training pads. And they're aligned using the writer-independent model, and then we throw away everything else and then just bootstrap all our writer-dependent models from scratch and train them up. And
You didn't use any of the
yeah.
cluster information.
Pardon me?
You didn't use any of the cluster information in this.
Here, in doing the alignment, you use the writer cluster model that it's closest to.
But
So you identify
that
that.
data along with this to train them.
No, right now we have not done that. Actually, we have been thinking about doing things along those lines because essentially we want to be able to sample into the writer cluster data for models that we have actually not good estimates for, and then augment the data and then use that in a writer-dependent training as well. So, and again, I just wanted to, I'm going to put these numbers up and I'll give you some thoughts on the kinds of, so these are 5 different writers I've picked, where the writer-independent error rate was anywhere from 37% to 60%, where actually the writer who had the 60% error rate was fairly consistent in their way of writing. It's just that the writing style was very different compared to the writer-independent system. So the key is consistency in the writing, and if you have a writer who's fairly consistent, then you get a fairly significant reduction in error rate when you go down to when you actually train up a writer-dependent system for these writers. We found a lot of the writers actually find that this is the people who actually bought the system. They do find that half an hour is what it takes to write this amount of training data, and it takes about another 45 minutes to train up the system. Gives them a fairly significant reduction in error rate if they're consistent, and they actually learn to be fairly consistent in the writing. In order to, and handwriting, mind you, is really far from being consistent. If you look, even if you're at your own notes, depending on the time of the day, how tired you are, your styles can change significantly. And we found that the same person trained, has error rates that change a lot depending on the kind of data set that they're writing and the time in which they're writing. Okay, so this is all I've talked about is for US English. We right now are actually looking, we've gone on to adapting this model for UK, English, French, German, Spanish, and Chinese and Japanese. So actually I'm not going to talk about Chinese and Japanese, but I just wanted to point out a couple of problems because I think one of the goals here is actually to point out some of the problems that we're working on right now. So first of all, Chinese was a major difference compared to US English because you don't have you have 6,000 characters in Chinese. So what you do in Chinese is we model what are called as radicals, which are these sub-character shapes. And that's what our HMMs model for the Chinese letters. And they are then strung together to form the character models. Another big problem in Chinese that we are actually working on right now is Chinese data is fairly seamlessly interspersed between English and Chinese. So we need to do language identification on a cluster by cluster level. So this is actually something that I picked up from a document that someone wrote where this person actually goes back and forth. Going back and forth between digits is very common. And also people write things like this, followed by date or price and number. So you would want to actually identify the language that the person wrote and then go back and then redo the recognition. So this is something that actually has to be addressed in Chinese if you have to sell any sort of note-taking application. We're actually concentrating a lot on Chinese because in China, keyboard is not a very easy form of inputting information into the PC. So you actually, they look for pen input as a way to replace keyboard entry. So this is potentially huge market there. and there's a need for this. In Chinese, actually, we already have cursive, traditional, and simplified Chinese working, and also for Japanese. Okay, and I'm actually not going to talk about, you all are fairly familiar with graffiti. So actually, in addition to doing let me just put up this slide that I had, you've all, essentially what I talk about is, you have the content versus, letter shapes spectrum. We've always traditionally worked in the completely unconstrained, open vocabulary, large vocabulary systems, writer independent versus writer dependent. But Palm was very successful because they had graffiti. I mean, it's simple shapes. It's very tightly constrained, and small vocabulary. And this is where they're able to get a very high degree of recognition accuracy. So actually, we've adapted our system to also on graffiti data. And in addition, what we've done is we've defined our own unistroke set. How many of you have actually used the graffiti alphabet here? Do you know what the graffiti alphabet is? Okay, so one of the big problems with graffiti is it's not a readable alphabet. I mean, it's meant to be for the palm, where you actually only look at the output. You actually are not reading what was written. So we've actually defined our own unistroke alphabet set that's keeping readability in mind, but it actually looks like shapes that you're familiar with. Okay, and actually I wanted to talk about just a couple of other things before I wind up. These are kind of the vision of the group and where we're going right now. So what I'd like to do is think of the vision as allowing users to effortlessly input and integrate handwritten data into applications. So the problem is document parsing and recognition. So this is a field that where you need to actually parse the documents into regions, in each one of which there's actually data of one kind that is contained. Multilingual recognition, of which language ID is a fairly significant problem that we need to address. Shape and gesture recognition. So for handwriting, you can't actually avoid doing shape and gestures, because typically shape input is what people use pen a lot for. So you need to also look into that. Finally, indexing for information retrieval. So as I said, I marked keywords in my document. Here's what people want to do. They want to write pages of data, like I've done, and let's say send it to an offline processor that does recognition. Maybe it's error prone, who cares? But the question is it good enough for doing retrieval? So let's say I send 10 pages of data off to a backend system and converts that into text. And now I'm actually write a word. So it doesn't recognize it accurately, but the question is, does it have enough information in it to do retrieval accurately? Finally, there's actually a lot of interest in doing embedded recognition. So, I was talking to Jan today. There's, people want to be able to do some sort of recognition on board that device. Right now, it's a down device where all the recognition is done offline. So the question is actually, can you do much more of recognition on the device itself? And finally, actually, right now, we've just embarked on an effort with the speech group to combine pen and speech. We're actually looking in a few months, we're going to have another variation of that's going to have a mechanism to input audio. So people want to take this for meetings and capture audio and handwriting streams. And the question is, how do you actually combine this topic by topic and provide it to a user in a way that they can easily search through and archive and retrieve. Okay. Finally, actually, if you're interested, we also have spent a lot of time using this for forms processing. So we have a huge amount of forms data that we've collected and done a lot of recognition experiments on that, which I probably don't have time to touch upon. I'm going to leave you with a few websites. So the first one is where there's a lot of work on our handwriting papers. That's research.ibm.com handwriting. Electric ink is our SDK and toolkit. So anytime you buy this device, you want to communicate with it, you can do so using the toolkit. Crosspcg.com has information on this device itself, how to order it. And that's my email address. So I have trained to catch at 6:15, so I'm actually going to find out. But you know, so I'd like to spend whatever little time I have to answer any questions that you have or issues. And you're welcome to come try it out. Yeah.
How do you segment words to characters?
Okay. So segmentation is done as follows. So in the beginning, we take a page and we look. So we segment line by line because we look for a new line. Within each line, we look for white spaces. So then we treat everything that's in between two white spaces as a cluster. So each cluster can be a set of words. And within that, we search for, it's exactly like a continuous speech recognition system. Look for a sequence of words within that cluster. So at worst, we have probably about 4 to 5 words in a cluster. So which is actually much simpler than the kind of lattices that you're looking at. So, it can't be definitely more than a line, but it's usually half or a quarter of a line. Yeah.
When you said that people prefer paper to writing in glass, is that a tactile phenomenon or the fact that they don't actually see what's being written as they write?
It's actually both. It's predominantly the first, which is the feel, the tactile, the feel of paper and the friction and so on that comes with it.
Have you done many experiments where you have a sort of pressure sensitive pad where you actually can have like a plastic interface where you actually do see the bitmap materialize as you write?
On the tablet itself, you mean?
Beneath the tablet.
Okay. Actually, there are tablets. There's a company called Kurda that makes a tablet like that, where you actually, there's a screen underneath. So as you're writing, you can see the ink. Is that what you're talking about?
Right.
Yeah, underneath it. Yeah. Again, they don't come. The feel of the pen on that on glass is not something users feel comfortable writing large quantities of data on. So, in fact, that is predominantly why IBM used to make these, what they call a 710T. They were tablets, actually that were used by insurance companies. These were full PCs in themselves that looked like a tablet with a screen. You write on it, and you could actually do recognition on board. And it's people don't like it. They don't like it because the feel is just not something that they're comfortable with. People have designed tethered tablets that have the right friction on them, but it's still far away from actually having something like that you can that people can use for this quantity of data input, for sure. Yeah.
It might be a stupid question, but have you thought of integrating this with a ThinkPad? Because it might be a good addition to the ThinkPad users. They could write on the top and on the back.
They did.
It's integrated.
So about 5 years ago, IBM did make those. So you could actually take the screen and bend it, fold it down, and write on it. Is that what you're talking
Just
about?
a clipboard on the back of the ThinkPad that you can just put a notebook on.
Right. Actually, thank you, but that's what actually 3 months, 4 months, it will be out in the market. That's essentially what we're thinking about, something along those lines. Actually having a thin ThinkPad with the crosspad. So the idea is, you can use the crosspad, when you actually don't need to do anything on your PC. It's just a data input device. But then, we can actually bring it up, and then when it's connected, you can input the data into any application that you need.
You spent a lot of time talking about how difficult it was to sort of take the sort of sequential sampling and then map it back into locations on, mapping continuations back to the original character.
Right.
Since you're sort of doing this in batch mode after it's been entered,
yes.
Is that really a difficulty?
It is difficult because people, the biggest problem is how do you identify the lines, partly because the pages shift quite a bit. So typically, if people come back and add data, it's usually not exactly where you want it to be. So you need to, if you actually look at this tablet, there's a lot of play in here. So there's a lot of, so when you actually come back and you want to insert words and so on, it's probably not in the right position. So actually identifying which line is closest to and estimating the line and go back and refining the estimate is what needs to be done. So essentially what we do is we go through first pass, and then we identify lines that we are sure of, and then the words that don't fall on any of those lines that are in a separate file, and then we go back and compute the score for its belonging to any one of the individual lines. And go back and refine the estimates again. Yeah.
When you talked about feature extraction in articulation points and the angles, it wasn't clear what you do when there's curvature, like a B. How would a...
So it looks for extrema points, so dx/dt equals 0 and dy dt equals 0.
But
so
a curve and a circle would be, they have the same extrema points.
A curve...
a U and a V.
A U and a V,
Same extrema.
Right, right.
How do you model the difference in curvature?
So the idea is that, for a U, hopefully if you we look at windows around these extrema points. So we actually capture the shape information in those windows. So if a V is actually very steep, you have a different set of features compared to a U. But if a person writes a V very much, if a V very much like a U, then that's definitely not something we can distinguish between. Did I answer that question? I mean, there are features that actually capture the curvature information in a window around the extrema points.
I understand, but at the actual tangent, it's a U and a V
Yeah.
have potentially 180-degree angle.
Mm-hmm.
So how do you sort of reduce the dimensionality of this curve to a single feature?
So we would have to, if there is no unique extrema point, so we would look for an extrema point if we can find it. So if the system cannot find an extrema at the bottom of the U, what it will do is if there are enough other extrema points to anchor the system, it will just use that and completely throw this away. So you're talking about if the bottom of the U looks flat, then you probably will not get a feature there, right? Because is that what you're talking about? Yeah. Okay. So if a U looks more like a square-like shape, so it's pretty much flat at the bottom, so you will not pick up a feature point at the minima. So because the shape actually looks very different. In that case, either we won't have a feature vector, in which there could be a problem with recognition. Or another thing we do is if you find that two feature points are really way far apart, we'd actually artificially put a point in the middle, because we assume that we have some problem either with digitization or computing the curvature points themselves. So we actually go back and insert points if we find that there's a large gap between two feature points in the original data. So we go back and actually insert these feature frames. Anything else? Okay.
Have you
Yeah.
considered using global positioning satellites?
It's interesting. This is somebody actually who's building a GPS sensor on a pen. And here's why they wanted it. They came, they said, there are people who repair in a shipbuilding or, and they actually have these documents. Ideally what they like to, they want to hold these documents and they want to use the GPS system as a marker to say, okay, this is the problem, I'm talking about, and give you more information on it. So, yeah, so presumably yes, but far away from getting the kind of accuracy that you need to make this happen. But actually, the ultrasonic, the pen that I talked about with sensors does triangulation-based methods to compute XY points. So that actually you'll probably see that in the market pretty quickly, where you have actually a clamp that you can put on any piece of paper that you have, and it has an array of sensors in it, and then it actually using triangulation measures the coordinates of the point.
Is it doing any work on, you were mentioning graffiti and coming up with stuff like that. Any work on discrete, like single character by character with the spaces in between lifting the pen and having a language model, say a bigram, a letter bigram, the replacements for this handheld?
yes, our system does graffiti recognition, and we have character engram models, so we could use it. The question is, if you're asking, have we actually ported that to any
But there's
platform?
also the problem of getting it down to the size that it would fit in.
That would probably not be easy. Typically, the system we have right now is about 2 megs, including all DLLs and dictionaries and so on. So I know the Palm has 8 meg, did you say? 8 or 10 meg?
Sure.
Yeah, okay. So, but even 2 is too much for the recognition module on that device itself. So, yeah, we would have to actually even bring it down to a smaller size.
Just quick, are there crossword effects on the character engrams?
Actually, I didn't talk about context-dependent cross-word effects. Okay.
You mentioned that you could get a good count for all the character bigrams.
Uh-huh.
And I was thinking, like in speech, we could do that if we only had word internal and physical.
Probably not as much in handwriting. We do definitely cross letter, so ligatures. Yeah, they're definitely very, very context dependent issues. But crossword, typically not. The only cross-word information we use is normalization baseline. So we assume that from one word to the other, these will typically not change the normalization factors and the baselines and so on. So that's carried across from one to the other.
How do you trace page changes? So if you want to go back and add something to the previous page?
Big problem. And so here's what we do. The ink stream is time ordered. So if the person does typically writing from top to the bottom, going on to the next page, doing this, then it's very easy to separate out because it's trivial. You're looking for it. If I write on this and I flip the page over and start writing again and keep doing this, then I can use simple heuristics like look for the 2 strokes, one which is at the bottom of the page and the other that's next, and probably there was a page change detection. But if you're constantly going back and forth and adding ink to a previous page, then it becomes a difficult issue. So unless the user actually goes back and also changes the page number on the device itself, it will probably assign it to a different page than the one that you intended it to be. Because for the system, for example, if you're writing here and you come back and add another word on the first page, it doesn't know. I mean, it's for it at the same position, it's the same thing. So it does not have enough of information to discriminate. This becomes very critical actually for forms processing because you're filling out fields if you want to come back and you're assigned to the wrong field. So there what we do is we use more information about the form itself to anchor this data better.
Wouldn't this problem be solved if you have just a scanner device, a very small scanner device that scans the pages after that? I mean, it can be like this, probably, because the handheld is very small. And then you just combine that information with your optical information, and you can actually have it very accurate.
Have a whole.
Okay. Something that slides on that.
Actually, there is a woman by name Lisa Stifelman. She has built a device where you have pre-printed pad of paper with a number, page number, which is barcoded on each page, and a little scanner that sits on top. So when you actually change the page over, it's constantly reading the barcode of the page. So what you can do is then, when you write an ink stream and you think it's page 7, but the barcode says, no, that's something else. So the barcode tag is constantly, being read in as well.
You have to buy all those kind of notebooks every time.
Exactly, that's the problem. So, yeah.
The complete drop of time information.
Yeah.
How much is
typically if you drop time, I don't know if you've actually run, because our system is so time dependent because features are time dependent and everything. So the other data point I can give you is OCR systems that don't have time. I mean, they do have other problems like, scan, image, degradation and so on. But no OCR handwritten system works for more than about 200 to 300 words with the error rates that you're talking about for here for handwritten data. So OCR, handwritten OCR at this error rate would probably work for about 200 to 300 word vocabulary, and it sharply degrades after that. So they're typically used for forms where you have a lot of constrained vocabulary in the individual fields. Anything else? Okay, thanks.